Hello everyone, we're Group 6 and today we will present our group project for this class, which is called Language Model with Temporal Author Representations. My name is Yuanyuan Zhe. Me and my teammates will introduce this project in this order. First, we'll briefly talk about the tasks and related works that we have researched. And then we will introduce the process of our implementation, experimental details, and result analysis. At last, we will conclude our project. So first, it is known that language models, which decide word distributions on the basis of context, is an important part of natural language processing, which is called NLP. But recent language models, from Word2Vec to Elmo, BERT, their fundamental idea is to use machine learning or deep learning structures to learn the representations from raw data. But languages are written by humans, and things like their writing style, their target topics, which all change through time. In order to learn a better language model, it is reasonable to use this additional knowledge, such as authors and the published time. So based on this idea, we choose the paper called Learning Dynamic Author Representations with Temporal Language Models as our main paper to implement. This paper proposes a deep language model which uses author representations learned from the knowledge, such as authors and their published time. And the model is able to achieve the state-of-the-art results in many tasks. Again, our project type is an implementation project. So after that, we did detailed research on the related works. We have read a total of 6 papers and related information to understand the background of the paper. First, from the perspective of language evolution in texts, previous works focus on temporal topic modeling or topic evolution through time. They used probabilistic models such as Haddon-Markov model or LDA, and there are also works on vocabulary evolution through time. But neither one of them is not strong enough to be language models, since they all lack of expression ability. And recently, some dynamic models try to make improvements, but it is still hard for them to combine with the language models. For example, graph-based models require a prior knowledge from the knowledge graph, which is not feasible in reality. Next, in the view of representation learning, which is language models, we also study some papers of famous language models such as Word2Vec and LSTM. After reading those literature, we gain basic understanding of the background, and then we dive into the paper and make our implementations.
Hi, I'm Wenze. Okay, next I will introduce Chapter 3, Implementation and Experiments. In this project, we use the Google Colab and Kaggle Notebook to implement this paper. And I will introduce the data sets. With the knowledge of language evolution in text and language models, we field studied 2 papers that inspire the main paper we have chosen. They are as the following. In the first paper, a graph-based scientific lecture dataset called Semantic Scholar is created. In the second paper, based on the New York Times dataset, a model that learns the repetition of word with tempo effects is proposed. And in this project, we use F1 microperplexity to evaluate the training results. Same as the paper, we evaluate the model with the 3 tasks. They are the modeling, imputation, and prediction. Modeling uses the whole data in the process of training, validating, and testing. The split process are done in a random state, and the restrictions are made to maintain the author name distributions in each kind of data. And the imputation for each author at each time step. The data only appear once in training, validating, or testing data set. This step can measure the interpret ability of the model. And the prediction for each author, models are only fed with the data in the first few time steps, and the task is to predict tests in the following time steps. This task is the hardest, and it can measure the generation ability of the model. And next, I will introduce the data processing. the original paper, lowercase the generals and newspapers tests in S2 and NYT datasets respectively, and they use the different models for tokenization with BERT and LLTK. Coopers using BERT for tokenization had about 45 titles dependent on the 800,000 tokens from about 1,000 authors. The distribution of the titles is not uniform, and the number of the titles grew quite exponentially along time from about 100 documents in 1985 to 5,000 in 2017. NYT Coopers using LTK for tokenization. During the process, this paper discards words appearing in less than 5 times. And our data of the process S2 Coopers and NYT Coopers is showing in this picture.
Hi, this is Cao Yufei, and I will give detailed description of the model. Generally speaking, our model can be divided into 2 parts. One is multi-layer perception, which is a dynamic model used to deal with temporary drafts when we update author's representation through time in the latent space. And another one is long-short memory, which is used to capture both language structure information and dynamic author's information. Into some details, the first formula was used to explain our test. First, we define author A and its publication timestamp T, where capital A is the site that contains all authors, and capital T is the time interval for each author. And then our test can be formulated as maximizing the likelihood of the whole lateral archive knowing the author and the timestamp. From the above formula and initial analysis, we can know the author and timestamp information we'll take into consider. But if we take into careful consideration, we can find the gap between historical publications and the uneven distribution of documents from different authors. And different times exist. Different authors may publish different publications at different times, which are all dynamic. So we use latent vector HAT to indicate authors and timestamp information. So the formula can be modified like the second one. This formula above expresses the probability of a document X for one long-short memory model with its author information A at time T. As the model structure above shown, latent vector HAT involves from times with a function F5, which is the third formula. As the author and timestamp information change, the condition HAT will have a corresponding change so that the following long-short memory model may differ as to the capturing dynamic change. In the process of updating HAT, we use a Markov transition function and also leave residual architecture for dynamic evolving. After being constrained by regularizing with an L2 normal, the dynamic formula is like the first formula. In another part of the whole model, we use AWD long-short-term memory model, which was introduced in paper regularizing and optimizing long-short-term memory language models. Since the recurrent connection of an RNA have been prone to overfitting, in order to counter this problem, Job Connect was introduced into AWD long-short-term memory. In Job Connect, each unit will get input from a random subset of the units within the last layer. Job Connect is applied to weight matrix UI, UF, UA, UC between hidden states, non-hidden states, or memory states. This discarding operation is only performed once before forward and backward propagation, thereby minimizing the impact on train speed, and is suitable for any standard black box RNA optimization implementation. By discarding part of the information of the weight matrix between the hidden states, the overfitting of the long-short-term memory connection can be prevented.
I am Ji Ming Hao. Then I will introduce our implementation of the LSTM language model. First, I will introduce the structure of the LSTM language model. The structure is as the picture shows. From the picture, we can see that what we build is actually a simplest one-layer LSTM, which inputs is the sequence without the end index, and the labels is the sequence without start index. Also, we can see that we use the output sequence of the LSTM as the representations of the output words. Then, with the ideas of the paper, we implement the LSTM language model with other information. The structure is as the picture shows. From the picture, we can see that what we do is to use a multi-layer perceptron to learn the representations of the input answer. And we use these representations as the start token of the input sequence. The author of the paper thinks that people's writing style will change with time, so timestamp is also useful in building the language model. So we also build the LSTM language model with other information and timestamp. The structure of the model we build is as following. From the picture, we can see that what we do is to use a multi-layer perceptron to learn the representations of the input answer. And we use a multi-layer perceptron to learn the representation of the input timestamp. Then we concentrate the outputs and let it go through one multi-layer perceptron. After that, we use the output as the start token of the input sequence. After building the three models, we do experiments on these models and the result is as following. The following is the FE micro perplexity of the model we built and the model of the paper on the different data sets. From the result, we can see that the performance of the model with other information is better than the simplest LSTM language model. This shows that the information of other does helpful in language model, and the model can learn the other representation. However, we also can see that the performance of the model with other information and timestamp is not better than the model with only other information. We think the main reason for this is because without any constraint on this timestamp and other information, the model cannot directly learn the representations of the answer in different timestamps correctly. Moreover, we can see that our experiment result is less than the result in the paper. We think the main reason for this is that we use the simplest LSTM as our base model. Instead of the simplest LSTM, the author of the paper used the AWD LSTM, which is the state-of-art model in language model tests. Besides, from the introduction before, we can see that the author's model gives a strict constraint to the timestamp, which each timestamp's author representation need to learn from the previous timestamp. This is also a very important reason why the performance of the paper's model is better than ours model.
Hello, my name is Liang Minghui, and now let me introduce the hyperparameter fine-tuning part. Hyperparameter tuning helps us to find the best model. In our project, we try to tune weight decay, learning rate, dropout, and some other hyperparameters. The results are shown in the table here. The first one is weight decay. Weight decay is a number between 0 and 1, multiplying each weight in the gradient descent with respect to weight. In other words, it is a kind of regularization, preventing overfitting of the model. So this parameter is useful, and we need to find out the best values, which is neither too large nor too small, and suitable for the model. After fine-tuning, we find that the performance will be better when weight decay is around 0.0003, although it is also influenced by different datasets and different tasks. And here is the learning rate and learning rate schedule. We are well aware of the importance of learning rate in model training. Learning rate is an important hyperparameter for deep learning models since it has impact on the convergence time of our models. If the learning rate is too high, it may cause divergence, while too small will lead to slower convergence. What's more, the constant learning rate cannot satisfy the model training very well. It is important to find the best learning rate schedule, and we can see the number of iterations without learning rate schedule and the number of iterations with linear learning rate schedule here. We find that when the learning rate is constant for 10,000 iterations and decreases linearly for 1,000 iterations, the performance will be better. And here is the dropout. When there are too many parameters in the model, but training samples are not enough, the model is likely to become very overfitting, which is common in neural networks. Dropout is a very effective trick to prevent overfitting, working as regularization tool. When we input forward, we may let the certain neuron stop working with a certain probability. The model will be more generalized using dropout, since it won't rely too much on some local features. In this project, we may focus on input dropout between RNN language model, output dropout, and weight dropout in RNN language model. And we can easily find that the models with dropout have better performance than the models without dropout. The result is consistent with our theory.
Besides hyperparameter tuning, we also try to make some modifications. Our focus is on how to combine the auto representation with LSTM. We try 3 methods. First, we try to similarly concatenate with the sentence. Next, we try to use it as the first token of the sentence. Lastly, we also project to hidden size and use it to initial the hidden state. As a result, the second yields the best result. We think it is because this method avoids overfitting problem.
Hi, I'm Shenqi. I will introduce Chapter 3, Analysis of Results in the Original Paper. This paper presented one perplexity, which is macro, and create perplexity for every corpus and task. And this paper created PCA and used keywords in each paper as labels to plot TSE in visualization. This paper also showed trajectories on S2 between all the authors in the latent space. Chapter 4, Conclusion and Future Work. In conclusion part, from the experiment results of naive LSTM-LM and naive LSTM-LM with author representation, we can say that the author information is helpful in language model. However, from the results of naive LSTM with author representation and the naive LSTM with author representation and time step, we can say that, actually, though people's writing style will change with time, if we want to use such kind of information, we do need to add constraints on the time. Otherwise, the model cannot correctly learn the representation of the author representation in different time steps and tends to overfit. Compare with the naive LSTM-LM and AWD-LSTM style, and relating setting that the paper use does improve performance quite much. Through hyperparameter tuning and model set structure modification, we can say that the best hyperparameter setting is here. And the best way to put the author representation to the language model is to project into token size and use it as the first token of the sentence. In the future work, the intuition of this paper is to combine additional knowledge of text into language model so as to generate better tasks. So better quality of additional knowledge can one direction for further optimization. With recent development in integrating knowledge graph into language model. In the future, we plan to construct the order representation using language graph to achieve a better performance. That's all. Thank you.